Okay, so we're going to get onto the new bit of proof that I think is going to take a little bit more concentration, so just make sure you're really listening carefully. We can do the last bit of proof, which is this thing that you'll have seen many times saying proof by contradiction. Now, you know, a contradiction is where you say that something is like the opposite to what it is. If you contradict someone, you say like the opposite kind of way around. So this is the steps that you take in a proof of contradiction. To prove that a statement is true by contradiction, the first thing that we always do is we assume that the statement is false, which sounds crazy, okay? I know it sounds crazy, but you just pretend that the statement is false. Then what you do is you say, okay, well, I'm going to see if this leads to some kind of contradiction. I'm going to see if this leads to something that makes me go, whoa, this doesn't make any sense. And because there's this contradiction that pops up, this means that we originally, assuming that the statement was in fact false, was wrong, which means that therefore the statement must be true. So let's just think about that really carefully about what the logic that's going on here. We're going to pretend that the thing we're trying to prove is false. We're then going to do some maths that will come up with something weird that contradicts itself and doesn't make any sense. Now, because it's contradicted itself and it doesn't make any sense, that must mean the thing at the beginning that we assumed was false is actually not the case. And if something is not false, it therefore must be true. Now, this is a rigorous way of proving things. Okay, you might look at this statement here that says, prove there is no greatest odd integer. And you might say like, okay, well, yeah, like there's a million, and then obviously there's 1,000,001, and then, oh, there's 1,000,002, and oh, there's 1,000,003. But none of those things are ways of actually proving something. They're just ways of you kind of reasoning with it in your head. And that's kind of what you do in this second step, where you prove that there's going to be, that would lead to a contradiction. So that's the kind of thing that we're going to do. So let's try and do this. By assuming that this is false, we're going to be able to do some interesting stuff. So it says prove that there is no greatest odd integer. So I'm going to assume, and you write this every time, assume for contradiction. So we're now saying, I'm going to assume that this thing is actually a lie. Assume for contradiction that there is a greatest odd integer. And let's say, I don't know, n. Now here's the part where we're going to prove that this would lead to a contradiction. But n plus 2 is also an odd integer. And clearly, n plus 2 is greater than n. So n is not the greatest odd integer. And that's a contradiction. That contradicts that we said that the greatest odd integer was n, and now we've said that n is not the greatest odd integer. So we've created this contradiction, this thing that's gone wrong in the question, which means that the original thing, that there is no greatest odd integer, is true. So let me just read through this again. We've said assume for contradiction that there is a greatest odd integer, say n, but n plus 2 is also an odd integer, and clearly n plus 2 is greater than n. So n is not the greatest odd integer, hence there is no greatest odd integer. So this is a proof by contradiction, because we assumed that the first thing was wrong. We then did something that then contradicted what we've just said, which means that the original statement was actually true. Do read through that one a couple of times. It is kind of weird. People last year found this kind of tricky. It's an odd kind of thing. So I'm going to try another one, okay? So this time we want to prove by contradiction that if n squared is even, then n must be even. Well, that just kind of makes sense. If you think of a square number and it's an even number, we know that its square root is also going to be even. But we just know that, but we want to prove it instead. So we try and prove this using a contradiction instead. So when I've said here the negation, Negation means the thing that we're going to try and say is becoming false, okay? So the false version. The negation means the false version. So the negation of if n squared is even, then n must be even, if a then b, is if a then not b. So let's assume for contradiction, and that's just saying that we're going to assume for a contradiction, we're saying we know this is going to be wrong. Assume for contradiction that if n squared is even, then n must be odd. So, if n is odd, then n equals 2m plus 1 for some integer m. So we're now playing around with the thing that we've assumed. We've assumed for contradiction that n is going to be odd, and we're now going to try and show that there's some kind of contradiction here. Well, if n is odd, then we get that n is 2m plus 1 for some integer n. So let's find out what n squared is. Well, n squared would be 2m plus 1 squared, which is 4m squared plus 4m plus 1, which we can clearly see is 2 lots of 2m squared plus 2m plus 1. So this must be an even number because we've got some integer being multiplied by 2 and you're adding on 1. Hence, n squared is therefore odd. But this is a contradiction to our assumption. Therefore, if n squared is even, I'm just writing out the original statement, then n must be even. So let's just go through the logic of what's happened here. We made a contradiction. We said if n squared is even, then n must be odd. Well, if n is odd, when you do n squared, you get an odd number, which contradicts the fact because we said that n squared was going to be even, but actually n squared was odd. So our assumption must be wrong, and therefore if n squared is even, then n must be even. Please read through this a couple of times, okay? These are strange sorts of ideas of logic, and I think the more you can read through this, the more it will sort of make sense to you. I'm literally just going to do lots and lots of examples. I think the more that I do, the more that you'll get the hang of how they're working. So this one is a strange one again. Each one I keep saying it's a strange one. You've used proof by contradiction to show that there exist no integers a and b for which 25a plus 15b equals 1. Okay, so you know what to do to begin with. We will assume for contradiction that integers a and b, I'm doing the opposite of this, so that they do exist. Integers a and b exist such that 25a plus 15b equals 1. Now there's a trick that we're going to do for this one, and this is quite a good proof to be able to try and do statements that are similar to this. Now we notice that both of these things are in the 5 times table. So if I do 25a plus 15b equals 1, if I do this divided by 5, I get 5a plus 3b equals a fifth. Now because we've assumed that the a and b exist to make this true, then, what should I write? Not there. Let's get rid of this. We know that because a and b are integers, so are 5a and 3b. But the sum of two integers is an integer, and our statement says that 5a plus 3b is equal to a fifth, which is not an integer. So we have a contradiction. Hence, just write the sentence again here, just to show that you've done the proof. Hence, there exist no integers a and b for which 25a plus 15b equals 1. So the reason we had to do this divide by 5 is to create something that was a non-integer that we could then compare to the integers that we had on the left-hand side here. So we needed to create a non-integer in order to be able to say two integers are making something that is non-integer, and that is the contradiction that we have. Okay, read through that again and see if that one makes sense. The marks that you get here are for assuming the contradiction, doing the bit of maths, showing that there's a contradiction, and then a concluding statement that you have, okay? So this one I think also came up in the practice papers. Use proof by contradiction to show that given a rational number a and an irrational number b, a minus b is irrational. First of all, I'm just going to break down what some of these things here mean. A rational number is one that can be expressed in the form a over b, where a and b are integers. I think we mentioned that a few pages ago. We mentioned that over here, okay? And irrational numbers cannot be expressed in that form. For example, pi, e, root 3, I don't know, root 2 minus 4. That's also going to be an irrational number. It can be a mixture of things as well. And the set of all rational numbers, we use this letter q, and the real numbers are r, natural numbers are n, integers are z. Don't necessarily need this, I just thought I'd mention it as a little point now, okay? So we're going to use proof by contradiction here. So we are saying that a rational number a, irrational number b, we want to show that a minus b is irrational. So the rational number a could be something like, I don't know, 4/5. The irrational number b could be, I don't know, pi plus root 2. And if we added these things together, you would still have an irrational number. Now that sounds sensible. That's the thing we're trying to prove, but we actually need to be able to prove this here. So, you can see my laptop's getting pretty tired now. What we're going to do is we will assume the opposite. So we will assume, for contradiction, that given a rational number a and an irrational number b, irrational number b, what's the thing we're going to be assuming? A minus b is rational. We do the opposite. Assume that given a rational number a and an irrational number b, a minus b is rational. So now we're going to do some maths. So let's let a equal, well, we've got a and b here, so let's say that a is equal to c over d, because that would mean it's rational. And the other one that we know is rational, because we can't write irrational numbers at all, so we've got to avoid doing it. And let's a minus b equal, well, we used c, d, why don't we use e and f? And I need to say where c, d, e, and f are integers, like we said over here, okay? So I know that a is rational. I've assumed that a minus b is rational, and I'm going to try and show that b, there's some kind of contradiction that we've got over here. So if I rearrange this one that we've got, I would say that a minus e over f is equal to b. And I'm hoping to come up with some kind of contradiction. Now, a is c over d, and we're going to say c over d minus e over f, two rational numbers, is what we're saying b is. So that would be doing cross multiplication, CF minus DE over DF is equal to B. And because C, D, E, F are all integers, CF minus DE over DF is a rational number. I'm going to come up here. Hence, B is rational. But this is a contradiction, because we've said that B was irrational. But this is a contradiction. So, given a rational number, I'm just going to literally repeat all of this bit here. Given a rational number A and irrational number B, A minus B is therefore irrational. So this one was weird. We said rational A, irrational B. We assumed that A minus B was going to be rational. You can only write rational numbers like this. You can't do anything with B. We can't write irrational numbers at all, so we have to only do rational ones. And then we're going to come up with this statement down here, where all of these are integers. This must mean that B is an integer divided by an integer, which is a rational number. But remember, we said that B was an irrational number in our assumption. So because we've got some kind of contradiction there, that must mean this thing that we changed is wrong, and A minus B must actually be irrational. So we've done the proof. Okay, we are nearly there. We've just got two more, and then I'm going to put some exam questions up for you. Now this one is incredibly famous. This is one of the most famous proofs that you'll come across. So we're trying to prove that the square root of 2 is irrational. We're trying to say that the square root of 2 cannot be written in the form A over B, where A and B are integers in their lowest form, okay? So I am going to actually take you through this proof. So let's assume, for contradiction, that root 2 is rational, i.e. the square root of 2 is equal to A over B, where A and B are integers with no common factors. In other words, it's a fraction in its lowest form. Remember, we wrote that over here. Where A and B are integers and have a highest common factor of 1, i.e. is a fraction in its lowest terms. So we're going to now play around with this. I'm going to square both sides. So I get 2 equals A squared over B squared. So we get 2B squared is equal to A squared. So this shows what kind of number is A. So A is an even number. Okay, we know that if this is being squared and then doubled, then it's going to be an even number, and we know that because it's a square number, that an even number, that A is also going to be an even number, because remember I think we did this proof earlier on. If n squared is even, then n must be even. So A is an even number. Let A equal to k, where k is an integer. So if A is equal to 2k, then you get 2b squared equals 2k squared, which is 4k squared. So b squared is 2k squared. So now we have that b is an even number for the exact same reason that we've got over here. We've got some number that's been squared and then doubled, so it's therefore even, and an even number, if b squared is an even number, then b is also an even number. So when at the contradiction. But, well, not but, because both A and B are even, they have a common factor. And this is a contradiction. It contradicts what we said earlier on. What we said earlier on is that A and B have no common factors. This is a contradiction, hence root 2 is irrational. This is a famous proof of the root 2 being irrational. So let's just take through again. We said it was rational for a contradiction. We squared it, and we came up with all this logic here to show that both A and B were even. But if they're both even, then they have a common factor. That's a contradiction. So what we assumed here for the contradiction was wrong. It was not rational. It is actually irrational. Okay, last one, and this is another famous proof. Prove by contradiction that there are infinitely many prime numbers. So you know what the first step is going to be. Even if you can't do the whole thing, you might as well get some of these marks. Assume, for contradiction, that there are finitely many primes. Let the list of primes be P1, P2, P3, P4, etc., all up to Pn. Now, let n equal P1 multiplied by P2 multiplied by P3 multiplied by all the way up to Pn. Then, n plus 1 equals P1 multiplied by P2 multiplied by all the way up to Pn plus 1. So you can see from here that n plus 1 is not divisible by any of P1, P2, P3, all the way up to Pn. If you just think about that, if you've taken all of these prime numbers and you've multiplied them all together, and then you've added 1 onto it, it won't be in the P1 times table, or the P2 times table, or the P3 times table, or even the Pn times table, because it's 1 bigger than all of those times tables when they've been one bigger than anything that would have been in that times table. So it can't be divisible by any of these things. Hence, n plus 1 is either hence n plus 1 is either, what should I say? What did I say here? It is either itself prime, you can see how I need to even check some of these things, or its prime factors are not in our original list. I'll show you what I was just looking at just then in a second. This means our list is incomplete. Hence we have a contradiction. And so there are infinitely many primes. And I think I'm going to just put some numbers here to make this kind of make a bit more sense, okay? So this is the end of the proof, but let's just pretend. Okay, so assume for contradiction there are finite many primes. We're going to assume that the primes are just 2, 3, 5, 7, 11, and 13. And we're going to let n be equal to all of these numbers multiplied together. So n is equal to, this is just to show you what's happening but with numbers. We're going to pretend that we know that these are all the prime numbers, and we're going to try and prove this is wrong. So 2 times 3 times 5 times 7 times 11 times 13, we get that n is equal to 30,030. Well, n plus 1 would be 30,031. Now, 30,031 is not divisible by any of these things here. So either this is a prime number, or it's got prime factors that are not in our original list. Prime factors are when you do like the prime factor tree. So I'm going to do my 3031. You can actually press shift and fact on these old calculators. It's if you press shift and then fact there, you may not be able to see it. You can see that 3031, when you break it down, is 59 multiplied by 509. So look, it's prime factors. Neither of them are in the list. So this means that n plus 1, it's not actually prime in this case. Its prime factors are not in our original list. 59 and 509 are not in the list that we have here. So this means that our list is incomplete because we didn't have the 59 or the 509. So we have a contradiction, and so there are infinitely many primes. What you might like to do is to try it with some other numbers instead and just see how that works out. I'm just going to block this off so that we know this is not a part of the proof, okay? You might like to try it with just 2, 3, 5, 7. You might like to try it with 17 added on as well. In fact, why don't I just... No, I'm not going to try that. You can try it with some other numbers and see how this is working. So here it is typed up so that you have this in the booklet. I've said, so you assume that there is a finite number of prime numbers, and we can list all the prime numbers, and there they are listed. We then consider a number n. They did it slightly differently. They just said that n was all of these multiplied, and they've added 1 on already. That's not a problem. When you divide n by any of the prime numbers, the remainder will always be 1, so it's not divisible by any of these primes. N must itself be prime, or its prime factorization contains only primes not in our original list. This contradicts the assumption that the list of prime numbers are all of them. Therefore, there is an infinite number of primes. So I guess the only thing that I would do different here is I guess we could have just changed this and called this n plus n and just put the plus 1 in here straight away. So that is the end of proof. There are a couple of exam questions that we've got here. I'm just going to quickly talk you through what you might do for some of these, and then I'm going to leave the mark schemes up. I feel like you've had enough of me today. Whoops, I'm not going to do that to insert an image. Here we go. So first we want to show this is positive for all real values of y. You're going to try and complete the square. That's only 2 marks, and you're going to use that to think about why that's true. This one it says e to the power of 3x is greater than or equal to e to the power of 2x. Determine whether Bobby's claim is always true, sometimes true, never true, justifying your answer. So just try out a few different types of values of x, maybe try some negatives, maybe try 0, maybe try and do some positives, and see if it's always true. Maybe you'll get sometimes it being true and sometimes not, and you'll end up with this one. Here it then says, Elsa says that for n as a member of, this thing here means is a member of, z with a plus, z stands for, we've looked at this a long time ago, positive integers. The positive makes it positive. If n squared is even, then n must be even. Use proof by contradiction to show that Elsa's claim is true. We actually did this one earlier on, so see if you can do this one. And here it says the sum of 2 different irrational numbers is irrational. Determine whether Ying's claim is always true, sometimes true, or never true, justifying your answer. So remember, irrational numbers may be things like root 2, but then also another irrational number is minus root 2. You could also have pi plus 3 and 3 minus pi. Think about what these would add to, what kind of number that might be, and see if you can come up with some answers that show whether Ying's claim is any of these things. And I'm going to leave the mark scheme here for you guys to have a look at so that you can read through them. So you might want to pause it and have a go. And then last of all here, we have another thing that's about sometimes true, always true, never true. They love to do these kind of ones. And last of all, proving that root 3 is an irrational number. Even though they don't say this one, you want to prove this one using contradiction. Okay? So I shall leave it on the mark scheme here for you to have a think about. You can press pause, and then the questions that you are going to try for me are from exercise 1A, and that's from the pure Year 2 textbook. Okay guys, I'll see you soon. Bye.